Let me give you an example. Follow the mechanism carefully. Okay. This, or as usual, we can take dilute sulfuric acid. Now, in the first step, it can be taken this way. Now the attack of H plus. C. We get CH3, C, CH3, CH3, then CH plus, of course. This becomes CH3. Right. See, this is a 2-degree carbocation. Okay. Now the 2-degree carbocation, check whether this can be converted into a more stable one. Yes, there is possibility of converting this into a more stable carbocation. See, 2-degree, which is less stable as such, undergoes 1,2 CH3 minus a shift, methyl shift. Okay, then we get this CH3, C. You get a positive charge here, CH, then CH3, then CH. See, for the different types of rearrangements, you can actually see our GOC video. Rearrangements are different types, like 1,2-hydride, 1,2-methyl, 1,2-phenyl. You got ring expansion, you got ring contraction. Now this is a 3-degree carbocation. A more stable one, right? Now this more stable one gets attacked by water molecule. Come on. That's it. See, here you get OH, H, a lone pair, and a positive charge. Okay. Then CH3, CH. Yes, we got the product almost. The last step is removing the acid catalyst. Come on. Minus H plus. That gives us the final. Yes. So this is how you get something which is, which we actually cannot imagine looking at the given structure. We expect the OH something at this position. But see, because there is a rearrangement, we got this product finally. So you need to be very cautious while going for acid catalyzed hydration. You get different types of carbocations. More specifically, remember, you need to know the stability order of the carbocation. Most often you come across benzyl carbocation also. CH2 plus. Okay. Now let us go for the same addition of water, but via some other means. Oxymercuration, demercuration. Right? That is what is generally given as OMDM. Oxymercuration, demercuration. Very simple, very simple. Now, let us consider the same propene. It will have two steps. This is mercuric acetate. Okay. Followed by the addition of water. Overall, this is oxymercuration. So this is when you get OH. Of course, you will come to know that this OH is from water. Knowing this is also very important. Like we are discussing things with deuterium also. And whenever it comes to water and deuterium, or when it comes to hydrogen and deuterium, we always get confused. So knowing the mechanism eases off that confusion. Okay. So of course we go for the clear-cut mechanism, but for now, check this. HGOAC. That's it. Now the second step. I mean demercuration. In this again, I have two reagents, sodium borohydride and of course an alkali. Come on, this is demercuration. So two steps. That's it. Here, this mercuric acetate is simply replaced by a hydrogen that comes from sodium borohydride. A very important thing to be remembered. So OH is from water. H is from sodium borohydride. Now, check the mechanism. See, overall, it is the addition of water. Let me give you the mechanism. Come on. This. And see, when mercuric acetate is added, say HGOAC, another OAC. We know that AC is acetyl. Acetyl. Okay. AC is acetyl. Now, Let me take this thing directly. Or otherwise, it can be taken this way also. First this, then this. Again, Markovnikov only. No problem, it can be shown this way directly. And just remove OAC in the form of OAC minus, because it is going out with the bonded thing. Minus OAC minus. Right. Now, look at this. You got this. But see, this HGOAC gets connected across the multiple bond. See this? And see, it actually gets a positive charge. Earlier it had only 2 bonds. Now it has 3 bonds, but even one lone pair was there. So now it gets a positive charge. Look at what has happened. You got something cyclic. This is called mercurinium ion. Now check this out. This whole area is been blocked. So no chance of attack from this end. Attack is only possible from the other end. That is, you can actually have anti-addition. Okay. Now, let me go for the next. Wherein, let me just add water molecule from the opposite end. See, this is according to Markovnikov. Point number 1, Markovnikov addition. The second thing is anti-addition. That means this is the regiochemistry, the direction specific. Where is that water molecule going and getting attacked? And in what manner? I mean stereochemistry. So Markovnikov addition is the regiochemistry. Regio means direction. Anti-addition refers to stereochemistry. Right? Now, let me give you the product. This one, this one. See, as and when the water molecule attacks, look at this. Okay. This one will still be there. HGOAC. Now remove H plus. Okay. This will be OH. And you still have this. So right up to this is oxymercuration. Now let me go for the second step, that is demercuration. So simple thing that happens now is the H replaces this. That's it. Straight away, we can go for this. Okay, of course, nothing but this. Now it is very clear that we got this OH from water. I mean from the first step. See this. This is how you got OH from water. And this hydrogen is from sodium borohydride. This is where your hydrogen is. So remember this. That is an important point. And overall, the thing to be noted is here you got Markovnikov addition and anti, no rearrangement. So that is very important. With acid catalyzed, it is M plus R. That means Markovnikov plus a rearrangement. No syn and anti in that case. But here it is only Markovnikov, no rearrangement. These are very important. Because we don't have any carbocation kind of thing in this, there is no rearrangement. Okay. Now, let us take some 1 or 2 examples for clarity's sake to see what regiochemistry is and what stereochemistry is. So coming to the first one. Let us take this into consideration. Overall reagent is HgOAC taken twice, water. In the second one, they have modified. NaBD4 is what is given. Okay. Now we know that we'll be taking OH from this and hydrogen from this. This all according to Markovnikov. Say this is the double bonded carbon that has less number of hydrogen. So let me just add things accordingly. So here I am going to add my OH, but at the same time, I need to follow anti-addition. So here it will be OH from water and okay, then here you get deuterium. Of course, there is a hydrogen already at this carbon. Okay, check out the things properly. You have added these two in an anti manner, right? And the addition of these two, especially the negative part, has gone to that carbon which has got less number of hydrogen. So is Markovnikov addition. Let me give you some clarity by telling you what regiochemistry is and what stereochemistry is. That's it. Now the second example. Now here there is an interesting thing. Look at this. D2O is taken. Even here also it is NaBD4OH minus. Come on. This is of course simple. You get OD from this and D from this. OD to this according to Markovnikov and D to this. That's it. Come on. CH3, C, then CH3. So this is C we have added OD, and to the CH2, D is added. So this is from D2O, and this D is from sodium borobutyrate. Just like sodium borohydride, this is butyrate. Okay. So this is about OMDM, oxymercuration, demercuration. So if you are okay with the mechanism, then of course you can tackle with such questions, especially the regio and stereochemistry. Now let us go for the third variety, that is hydroboration oxidation. Okay. The same addition of water, but again interesting. Propene is taken again. The first step is hydroboration. Let me take BH3 THF. Right. So this is meant for hydroboration. The first step. You know, in this case, because we got 3 hydrogens in BH3, let me consider 3 molecules of propene and see, we'll be getting trialkyl borane. We'll show you how when we go for the mechanism. So this is trialkyl borane. Now this trialkyl borane in the second step, that is oxidation, gives the final product. Look at the product. Of course, along with that we get borate. Now this is meant for oxidation. So hydroboration and oxidation. If you want what THF is, I mean what the solvent is, this is the solvent. Tetrahydrofuran is the solvent. Now let us go for the mechanism. Very, very interesting. Let us divide the mechanism into 2 parts. Hydroboration and then of course oxidation. We know how to add BH3. This is how it has to be added. This of course goes here, and this gets connected here, or you can actually show it this way. This of course comes here, no problem. So this is what I say as a sin addition, because addition is from the same side, this way. Okay, now we get a transition state, CH3 CH, a bond to be formed, then a bond is there, this is going to get broken. It has to be CH2. Now CH2, then a bond to be formed here, this bond is going to get broken, right? So this of course is the transition state. Forming, breaking, forming and breaking, that's it, right? Now come on, CH3 CH, this becomes CH2, or else let us write it very clearly as this, then this CH2 BH2. Yes, see, this hydrogen is from BH3. Yes, who is that? Now here we got monoalkyl borane. Aravind. Okay. Now this is how we get monoalkyl borane. In the first step, but still we got two hydrogens here. Even these two can be replaced. So let us consider two more molecules of the propene. And of course, we get this. These all hydrogens are from the BH3 only. Every time a hydrogen gets connected, CH2 will always be there. Overall, you will have three such things, and this boron. So this is how we get trialkyl borane. Okay. In general, it is simply represented as R3B. This is the alkyl group that you get. Okay. And remember, this hydrogen is from the BH3. Okay, done with the first half. Now the second half is oxidation. Wherein we have hydrogen peroxide and OH minus. Come on, let us take hydrogen peroxide this way in a proper manner, then the OH minus. Now this OH minus abstracts this hydrogen in the form of H plus, and this will come here. Then we'll be getting HOO minus. This is called hydroperoxide ion. And of course, water molecule. This is hydroperoxide anion. Okay. Now the trialkyl borane comes into picture. You know, boron has got only 3 bonds. That means only 6 electrons around it. So is a Lewis acid. So is an electron pair acceptor. Come on, let us use our hydroperoxide ion. Right? Yes. This way. R, B, R, R, O, O, H. Okay. Now, after this, the OH minus is last. Okay. Be little cautious. R, B, you got an R, then this O to which the R group is connected. Of course, OH minus is last. Do the same for 2 more times. See, we get RO, RO along with this old RO. This is a kind of ester called trialkyl borate ester. Now this OH minus again comes into picture. From the hydroperoxide, we got this OH minus. Will now attack. One goes up. We get R, O, B, OR, then of course this OH. Using the alkoxide that has gone out, OR minus has gone out now. Let us use it. Using this RO minus, come on. You take out the hydrogen, concentrate on the OH group. Okay. RO minus and this H plus. And of course, this comes here. Do the same for 2 more times. You will get the final product. RO, B, OR, and this O minus. Along with this, of course, we get alcohol. See, the same thing has to be repeated for 2 more times. Finally, you will be getting 3 moles of the alcohol. Along with that, BO3 minus 3. Everything will be like this. Even this also becomes O minus, this also becomes O minus. And the R groups are removed in the form of alcohol. First OH minus, then with RO minus. This is how you have to repeat the steps for 2 more times. And finally, you will get the alcohol. Hope this actually gave us the clarity that the OH group that we got is from the hydroperoxide. And here, the overall thing is anti-Markovnikov addition. So the regiochemistry is anti-Markovnikov addition. Then the stereochemistry is, of course, syn addition. Within the anti-Markovnikov addition or overall, I can also give you one more point. The thing what we have added, hydrogen is from BH3 and the OH group is from H2O2. That's it. Final.